This is a CFD simulation. Beautiful, isn't it? But here's an uncomfortable question. Do you actually understand a single thing the software did to produce it? For most engineers, the honest answer is no. It's a black box. Today, we break it open and run the entire CFD workflow ourselves in plain Python. Here's the surprise. For a basic CFD problem, you need just 2 Python libraries. NumPy does the heavy lifting, the grid, the equations, the solving. Matplotlib turns the numbers into the picture. Later in the series, SciPy joins in for large, fast solvers. But the core idea needs only these 2. Step 1, the domain. This is simply the physical region we want to simulate. In Python, a domain is nothing exotic. It's just coordinate arrays where the nodes live along each axis. NumPy's linspace builds them. That spacing, dx, is what mesh resolution really means, how far apart the points are. Step 2, the mesh. We chop the domain into a grid of nodes. And here's the elegant part. In Python, for a structured grid, the mesh is just a NumPy array. No special meshing software needed. MeshGrid gives the coordinate of every node. And this array, T, holds the temperature at each one, the very thing we're solving for. Finer mesh means more accuracy, but more nodes to solve, so more cost. That trade-off never leaves you. Step 3 is the heart of CFD, discretization. Our governing equation is the Laplace equation. We can't solve calculus at every point. So we replace those derivatives with simple arithmetic between neighboring nodes. Do the algebra, and the result is beautifully simple. Each interior node becomes the average of its 4 neighbors. This is called the 5-point stencil. We'll derive it rigorously from Taylor's series in the next video. For now, just feel how natural it is. Step 4, solve. We apply that averaging rule to every node, over and over, and watch the heat spread. Notice, the whole interior updates in one line of NumPy slicing. No slow loops over every node. And we track the residual, how much the field changes each sweep. When it shrinks to nearly 0, we've converged. There it is. The field has settled. That is a converged CFD solution, computed entirely by us. The final step, interpret. The numbers are done, now we read them. And that glossy contour the commercial software showed? It's just Matplotlib, plotting this exact array of numbers. One function call turns data into the picture everyone recognizes. Hot at the top, cold below, spreading smoothly. That's not magic from a black box. That's 5 steps you can read, line by line. Remember the black box from the start? Now you know exactly what was inside it, these 5 steps. And here's why opening it matters. At every step, the software made a choice it never showed you, choices that decide whether your answer is right. When you've built each step yourself, those choices stop being mysteries. That's the whole point. Today we did the whole pipeline on a simple heat problem. From here, the series goes deep on each step and the complexity climbs. Same 5 steps every time, just more physics, more rigor, until you can build a real fluid solver from nothing. The starter code is linked below, free. If this is how you like to learn engineering, subscribe, and I'll see you in the next one.